Okay, thank you everybody for being here. It is AJS. We speak with Fabrizio Caragiulo, the PhD student at SISSA, is about to defend the PhD in a couple of weeks. Okay, and it's an introduction of what will be this defense.
Thank you. Very happy to be here. And my aim for this talk is twofold. On one side, I'll try to introduce some of the terminology that will be then present at my defense, so that people won't be too scared about the technicalities. And the second is to introduce also to a public of non-specialists, specialists to the ideas surrounding the paradigm of the renormalization group, which is like a state-of-the-art paradigm for the study of complex system and more in general to perturbation theory of very singular objects. So I'll start with a GIF. Which doesn't. Okay. And every physical system admits a different description at different scales. So every description which tries to be accurate should take this into account. To formalize it, we can imagine to substitute as a mathematical description of an object, to substitute a description with a family of descriptions of an object. We can think about a family of measures, a family of PDEs, each with its own parameters. And so the our object of study will be this family of objects. And the first question that one could ask is how are these different descriptions related with one another? And sure enough, the difference between larger and smaller scales, we can think about energy scales or length scales. The distance between larger length scales and smaller length scale, or vice versa for the energies, is that by definition, almost the bigger length scales are made of smaller length scales. So the relation should be one of some kind of averaging. So the description at scale L, bigger scale, should be obtained in some sense by averaging or taking account of the smaller scales. And this operation of averaging should be satisfy some group-like properties, in the sense that the description at scale L should be the same if we start at scale L prime or scale L second, and then we average in both of them till the scale L. And so this operator or this operation area should act on some space of theories. They can be functional measures, PDEs, whatever, transforming one theory of one kind in another theory. Usually, to treat it mathematically, we suppose that the theory must be of the same kind, and after the operation, it will have, let's say, the same general structure, hopefully, but different, and they are so-called renormalized parameters. So if you have like a PDE of a hierarchy of PDEs, all the coefficients should change after each iteration. Of course, in the ideal limit where our theory is already defined in infinite volume, then this averaging operator should again produce a theory in infinite volume. So we could think about it an operation acting on the same space of theory instead of like theories on a volume and transforming them in theories on a different volume. In this sense, in that case, it could be a real semigroup instead of being just this algebraic group-like structure. But still, it's never a group, and it's like an historical naming. And I would like to start with a concrete model, maybe one of the simpler one, when some kind of where we can see already a great variety of phenomena appearing. The Ising model is simply described on a lattice, so we can with a two-dimensional lattice. infinite dimensions, and attach to each side of the lattice a sign. So it can be a plus or minus sign. To each such configuration of signs, we apply an energy or a weight, which is this one. It's the sum of all nearest neighbors. So this tilde defining nearest neighbors. So those stars of nodes on this lattice connected by a length one segment. And for each of these couple of nearest neighbors, we consider the product of the spin times minus j, where j is a positive constant. As such, the energy is minimized by ground state with uniform spins, so where they are all or minus one or plus one, and all other states have higher energies. Moreover, usual one consider the state at final temperature, which actually is mathematically is very standard to describe it by taking a Boltzmann weight for each configuration, spin configuration sigma, and attach to each configuration sigma a probability which is proportional to the exponential of minus beta, the energy of the configuration. So we can see that configuration of higher energy are exponentially penalized, but the more beta goes to infinity, the more, let's say, the temperature goes to zero. So beta is called sometimes the coldness, and it's the inverse of the thermodynamical temperature, and the system tends to focus on the ground state. While as beta goes to zero, the temperature goes to infinity, and all state of every energy tend to be equally possible. So we have two competing forces. On one side, the energy, if we try to minimize it, favors aligned spins, while the temperature, when it's high, tends to disorder the system. So we can see a nice video where the three different behavior of the system are visualized. First, we start for a system with low temperature and high beta, so that the system tends to concentrate on uniform state. And the bigger the average transformation are taken, the more the system tends to be completely homogeneous. On the other side, for high temperature or small beta, the system tends to be completely noisy, but there exists a singular value, critical value, where the system is still scaling variance, but present not a trivial behavior, but this kind of interesting and non-trivial scaling variance. From a mathematical point of view, how can we distinguish these three behaviors? Well, one way to distinguish it, very common in statistical physics, and it could be also interesting in for other areas, is to consider the so-called correlation function, which are simply the expectations value of the spin function and combination of polynomial or spin function with respect to the measure introduced before. And one can show that, at least for the two-dimensionalism model, quite explicitly, that the decay behavior in the distance x minus y of these correlation functions is really dependent on the temperature. And indeed, they decay exponentially for all values of beta, except for a single value where they decay polynomially, I believe as the power minus 1/2, maybe, in two dimensions. Bruno? No. Anyways, as a polynomial. And this is a way to detect the fact that the system is undergoing a phase transition. A few mathematical results. As I said, in two dimension, the model is exactly solvable. And the solution was first given by Onzager and was a surprise to everybody because nobody thought that it was a model anyway complex with infinite variable and so on could be solvable exactly. And so that, for instance, in two dimension, this beta c is actually an explicit number, is a hyperbolic arcotangent of square root of 2 minus 1 for some reasons. So is, huh? Are you sure? No, no, the critical temperature. No, arcotangent, I believe, arctange, I believe, square root of 2 minus 1. Okay. And then Schultz, Mattis, and Lieb managed to, I mean, the solution was surprising, but it was also unreadable. Was like 20 pages of mysterious computations. And so it took 20 years of work to recast it in more reasonable form. And basically, the modern solution, because it hasn't changed basically from the time, is to recast the Z and the measure of the AC model in terms of determinants. Actually, they are Pfaffian, but Pfaffians are square root of determinants, so I'll say just determinants, which are manageable and more explicitly computable. In four and more dimensions, instead, there is only the noisy phase, so the system always converges to a noisy system or to a noisy system on large scales. In dimension three, it should undergo a phase transition, but as far as I know, there is no really any idea on how to proceed in this case and prove it. And so it stays open as one of the big mathematical challenges of present times. So in any case, I mean, I said that there is no idea, but actually there is some kind of idea. The general idea of the complex system is this one of a renormalization group, and in the sense, mathematically, it's an iterative multi-scale analysis where we want to perturb. Okay, I'll say a little better. The idea is to recast any system as a perturbation of known or more treatable systems, which are usually determinants or Gaussian measures. And when we see the system as a perturbation of determinants or Gaussian measure, we try to do a multi-scale analysis because this system, this simpler system, these simpler objects, determinants and Gaussian measure, have good properties on a good recursive property, which can then be used to set up these inductive procedures. Inductive procedure. And I want to say another thing that yeah, I believe in that in three dimension one could also recast the system as determinants, but determinants plus other terms, maybe. Yeah, Pfaffians and other terms, which when that one should study the perturbation around the objects. I'm not 100% sure of this, so I didn't write it. So I won't say, okay, we are being recorded, so we'll stay forever. But and yeah, the problem is also that usually these objects, while being well behaved, they are still singular. I mean, we think about the Gaussian measure associated to the Laplacian. It still has infinities occurring, so it's not, yeah, it's a maybe in the limit, it's a measure on an infinite dimensional space, so it's not the nicest object ever. So the complicated part is also that this allows to perturb singular objects, and which is very non-trivial. So we'll now speak about the Gaussian measure and see why they are helpful and they allow to set up a multi-scale inductive procedure. If we take a simpler set, so let's say a finite set, or more precisely, a lattice like this in dimension D, so a cubic lattice in dimension D, then a Gaussian measure is simply a measure for with each variable for each with one variable for each node of the lattice. We call the variable corresponding to site x phi x, and then we have the exponential of quadratic exponential of the variables phi with the quadratic form, whose matrix is called the covariance matrix, and should be positive, definite, and self-adjoint. So in most cases, we can think about the C to be the inverse of discretized operator, like the Laplacian. And so taking some infinite volume limit or continued limit, one can recover the Gaussian measure associated to general quadratic form on infinite dimensional spaces. But we'll stay in a discrete setting for the moment, so this problem won't arise till the end. The fundamental property that make Gaussian useful in this multi-scale analysis is their additivity property or stability under convolutions, which is basically consequence or equivalent to the fact that the algebraic sum of Gaussian variables is still a Gaussian variable. And this property can be stated as follows. So whenever the covariance matrix is the sum of two matrices, both invertibles and positive definite, so each of them still define another Gaussian measure, then the integration of any polynomial find fields, let's say, it's also more general than just polynomials, with respect to the original Gaussian measure can be decomposed in two-step integration. The first one with respect to the first measure induced by the matrix C0, and the other integration with respect to the other matrix which was present in the decomposition of the covariance matrix. And so we see that this property is already self-evident. I mean, it's not that I want to say that it's self-evident, its usefulness, because we can already see that if C is in some sense becomes singular in the infinite volume limit, it already shows us how to set up a multi-scale analysis. We say first we consider a truncation on some shells of values, say, and we decompose our integration in first step and the second step. After the first step, we have a new integrand, and we do another decomposition. And so in the end, we decompose C as a sum of terms, and we can decompose our original integral as a sum of a series of integrals, but at each step we have a good definition. And this is the first property. While the second important property is that whenever we have the integral of a polynomial in the phi, it's explicitly computable. So for instance, if we have as a sum of pairings of variables. So we can now do a little bit of graphical representation, because if you have, for instance, the integral defined of phi is 1 till it's 4, this integral can be explicitly represented as a sum of the pairings of the variables. So think x on 1, x g1, I2, x j2. But in turn, this can be represented graphically. We can put, for instance, a dot xi for each of the variables, and a half line, half segment, x1, x2, x3, x4. And the way to obtain all the contribution is to join half of one segment in all the ways. So we have this one, we have this one, and we have roughly this one. And so for a four-term polynomial, for the polynomial, we have this three contraction over three terms. And basically, this is what they are called in physical literature the Feynman diagrams. we have also a nice, the moral here is that we have a nice representation of the result of the integration of something against a Gaussian measure. Still, there are some problems. Always there are problems. So we start to tackle the simplest one of them. Let's consider now as f not a polynomial, but the exponential of a polynomial. A polynomial which is local, so is a sum of each polynomial for each x in our omega set. And to take to have an even more explicit example, we consider the polynomial, which is the fourth power. We can then expand the exponential into a power series. We truncate at some power big N, and so we have a remainder, and the first n terms are integral of power of polynomials. We can then treat according to the rule of couplings and joinings of edges. In this case, moreover, all the x1, x2, x3 are equal. So we have some extra counting in the sense that many terms are equal between themselves. So at first order in lambda, we have all these three terms are equal. So we have three times c squared xx. But at second order, we have many different terms, I mean, three different terms, but which are more complicated combinatorics, which again can be computed with the same idea as before. And to better represent this, we can now use a slightly different representation where we use a different node for each different variable. So since we now at second order we have two variables x and y, use a dot for x and a dot for y, and we attach the number of power of each pi we have x as variable, which are 4, and the same for y. And then we have to count all the way to join the half edges that we have at our disposal. So for instance, the term cxx squared, cyy squared are those joining all semi-segments of related to the same variables. If instead join something like this, then we have a term pxy corresponding to this line, a term pxy corresponding to this other line, and then one pxx and one cyy. It then goes to the second argument. And then if we count all the way to obtain this term, we obtain the combinatorial coefficients. So nice, not so nice, because C is clearly a singular object. So it's clear that if C is translation invariant, sum over X will obtain infinities. But also CXX, as Simone told me, I reminded this morning, can be singular in any case. Also, if we are not taking the infinite volume limit, because maybe our operator which are inverting. So if we have C, which is the covariance associated to a second order differential operator, maybe it has zero modes or modes which are very close to zero. So C is not that much nice, it's singular. But these are, in some sense, spurious divergence. They are, I mean, they are not spurious, they are natural. They can be thought as like the divergence that there is when one is integrating periodic function over all R. If we integrate a periodic function over all R, unless the integral is zero, it must be infinite, obviously, because we have really the object we are considering is an infinite object because I mean, a periodic function over all R, of course, must be infinite integral if it's not zero. And so if we have a translation invariant object, of course, the sum over x of its coefficients must be infinite. Or also, if our starting point C is already singular, of course, we have to have singularities. But since the singularities, they are so natural, there is also a natural way to cancel them. To cancel them, not in the sense they are in the same way that when one is considering the integral of a periodic function over R, one recognizes that the object of interest is not the integral over R, it's um, the average integral over one period. And in some sense, one recognizes that the real object that one should study is the so-called normal ordered polynomials, which are obtained by subtracting to a polynomial some lower order polynomial, which are exactly those ones that cancel the product and theory. So they must be obtained through reverse engineering in order to cancel this. Like when we have integrals of periodic function and so on, one has to observe why there are infinities of this kind and then remedies them in a sensible way. So these, let's say, are the first kind of divergences, natural one. They are not only the only natural ones, because if we recall the definition on the Gaussian measure, we see that the Z normalizing factor, of course, diverges. So we take an infinite volume limit of our set omega. Of course, our Z should diverge not only uh, should not only diverge, but should diverge in a way which is exponential in our volume. So, for instance, it's obvious that this factor should diverge, and in this physical sensible. So it's not, in this case, this divergence should not be cured at all. It's natural. And in this case, is again, the natural objects are those which, let's say, compensate, but not only compensate, they recognize these natural divergences. So, for instance, it's expected that the free energy instead should be finite and converge. And the free energy is exactly the logarithm of z. So if z diverges exponentially in the volume, we have something which should be, in some sense, proportional to the volume, and then we divide by volume. And this quantity should naturally converge. And this, again, in the same sense, we recognize which are the quantities which are naturally diverging and study instead appropriate averages or instead consider other more sensible quantities. Last, I will just say en passant and extremely fast that also determinants can be recast in these Gaussian settings. This can be understood for the moment just as an algebraic trick, where one introduces a set of anti-commuting variables. So these phi x, phi x2, phi x1 are just anti-commuting symbols. They are symbols with the properties that if you swap them, you get a minus sign. And then you define operators on the vector space generated by these symbols and their products. And this operator simply cancels with a sign the corresponding variable. So this integral with respect to psi x1 has the behavior of canceling psi x1. So more precisely, what we do is to swap. If we have the integral with respect to psi x1 of something containing other variables, and then it appears psi x1 with first anti-commute, the operator with the other variables, so getting one minus sign for each time we anti-commute, and then when we are in front, so the second case, we are exactly in front of psi x1, we cancel it. And of course, if psi x1 is not present, we get 0. Moreover, so if everything anti-commute, not also that psi square is always 0. Because for anti-commutes with itself, it means that twice the psi square must be 0. And also that if we consider, we can consider then exponential this Grassmann symbol, which are simply defined through the Taylor series of the Taylor's expansion of the exponential, which in this case, since we have this property, it actually truncates to a polynomial. Because if we have a finite number of variables and we take sufficiently higher powers, at some time we'll have to have a variable which will be at least squared, and then we get zero. So the exponential is defined through a power series, but it's actually a polynomial, so it's of course well defined. And if we want define an exponential measure in this way, which is formal, but it still makes sense, then one gets that the integral of the of the measure with covariance c to minus 1 is exactly the determinant of c to the minus 1. And moreover, one can prove these are just basically consequences of properties of determinants, that if C is the sum of two matrices, here we don't require a positive definiteness. In some cases, it's not even necessary to be invertible, but let's say that are both invertible, then we can get again an iteration property, like before for really Gaussian measure, and also an analogous of Wick theorem holds. So I won't say anything more about Gaussian variables, but since I want to do an introductory talk, I believe it's important to say that these multi-scale techniques is also analogous for determinants. So if you deal with determinants in some part of your life and you have complicated problem about them, maybe this could be helpful also for you. And now let's go to the third and last part of this talk, when we investigate how the Gaussian measure behave under of course, general Gaussian measures, we don't know actually. But for most Gaussian measure of interest, we can say something. And we focus on our main example, which is the Laplacian and its inverse as a covariance matrix. And let's say that we write it as C0 plus C less than 0, where C0 projects on Fourier modes greater than something, and C less than 0 is the projection on the rest. Of course, this is well defined because the Laplacian and the discrete Laplacian are diagonalizable in Fourier space, so it's easy to make a projection on Fourier modes. It's all well defined. And also another property is that if we integrate just the Gaussian without any other terms, it's completely factorized because all the variables are in the matrix is diagonalized, and so all the modes are independent. So we can consider separately the integration with respect to C minus 0 and respect to C0. So let's try to integrate with respect to C less than 0, which is then the integration with respect to modes which are less than gamma. Okay, I lost a 2 pi, but less than 2 pi gamma. Of course, the Fourier transform of the lattice Laplacian is 2D minus cosine of ki for each variable I. I don't know if it's obvious, but let's say that it's Laplacian is simply let's say on n. So in one dimension, is simply a second discrete derivative. And if you do a Fourier transform of this quantity, you get 1 minus cosine. And if you have 1 for each variable, you get 2D minus cosine. Okay, now it's 2 minus cosine. There is a factor, sorry, I got also a factor of 2. You get 1 minus 2 cosine, or 1 half over or minus cosine. So there's some ambiguity about a factor 2 depending on the various conventions. So, yeah, 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 I don't remember if I wanted to take it, the factor 2 or not. Okay, anyway, yeah, okay. And then the heuristic reason is to rescale also the field phi by a power gamma to the W to be determined, so that the, um, the integral becomes comparable to the full integral. So we want to have in the end something which is comparable to the integral with respect to the whole covariance. And this is done by two observations. The first is approximating the 2D minus cosine of k by its Fourier series. So we approximate it by k squared, which is exactly true for the Laplacian on R, but in this case it's only approximately true, but it's still approximately true. And this grants us with the factor gamma to the 2. Then we scale also the variable k, and since we are in d dimension, we get a factor gamma to the d. And then we have the minus 2w by the rescaling of the field. If we want to have exactly a factor of 1, then w must be such that the exponent of gamma is 0. So we get w equal to d plus 2 over 2. If you go instead in X space, then after taking a Fourier transform, phi scales dually by delta, which is called scaling dimension of phi in X space, which is the dimension of the space minus W, which is, let's say, the scaling dimension in Fourier space, and which is now d minus 2 over 2. This is an important number. The idea is that if we have a perturbation of a Gaussian, each field phi behaves like a rescales with this exponent. And so each power of phi rescales by k delta. When we actually rescale, we have a k delta factor given by the scaling dimension of the field plus a delta, plus a d, which is the scaling instead of the Lebesgue measure of the discrete measure in X space. So the idea is the following, that whenever d minus k delta, so the dimension of the space minus the scaling dimension of the fields that we are considering, the field that we are considering, or they say the scaling dimension of the object we are considering is negative, after a scale transformation, the term tend to decrease. So it's well estimated, it's well bounded. And in the renormalization group jargon is said to be irrelevant. Of course, irrelevant doesn't mean that it's completely negligible. An irrelevant term becomes irrelevant in the sense that it's completely negligible only in the limit. But as long as it is not exactly zero, it influences all the other. But the idea is that it's quite boundable, so it's not really the source of the problems. So let's consider the example of just the polynomial phi to the fourth in 4 dimensions. Yeah. No. No, I don't know what do you mean.
the system also. So we want to expand again in order to have the system.
Yeah, yeah, I in the beginning, but yeah, I get this. This is an spirit of what I said in the beginning, but this was just focusing on what is GAM. I mean, here it's not that I really want to rescale. Just wanted to be an heuristic way to determine the scaling dimension of a field.
You are getting the same because you want to go back to a theory on the same sector, and then you will rescaling because you have a smaller ball now because you iterated more on the human model.
Mhm.
So you iterate now balance, you expand columns, and then you want to go back to the original situation.
No, yeah, yeah.
And so if you want to compensate the transformation of the column, also the filter to transform. Yeah, but they have volume changes. The volume changes that.
Yeah,
I mean,
I wanted to say it in a finite volume, but then there are problems, no? Because of course in infinite volume you have exactly k squared. You
So you put a off, and then it's not a matter of having two columns, one matter of with a certain amount of momentum that's allowed to integrate out, you forget about some of that, but then you go back to a theory at the same
Mhm.
time.
Mhm.
So it's not the volume with the space, but it's not the moment.
Yeah.
If you want on the physical space, what does it mean? It means that you are essentially space here. You want to take out is like from a single start of your lattice, you take a block of a single size, okay? And then now the spacing is double. So if you want to convert to a lattice of the same size, you have to
Yeah, so I said we wanted to have we choose the scaling to have the same covariance, but it's important to mention. I don't know if people can hear you. So it's worth mentioning that one can also see this as a rescaling necessary to that we rescaled in order to compare on the original volume of definition. Okay. Okay. So let's see how this plays out in the example of the fourth power in 4 dimensions. Then we see that we have the object of interest, the number that determines relevance of irrelevancy is 4 minus kd, and d is equal exactly to 1. Recall, d is, sorry, delta is dimension minus 2. So in case of dimension 4 is 4 minus 2, that is 2 over 2, which is 1. So you have that delta, the scaling dimension of phi is 1. So 4 minus k delta is exactly 4 minus k. And so all polynomials with the exponent greater than 4 are irrelevant in the sense that they have coefficients that tend to decrease with each scale transformation. And at least heuristically, the terms which one should really worry about are the square, phi squared, and the fourth power of phi. And this is the final idea and the final element that's still missing on this Renormalization group idea. So we decompose the covariance in 2 steps. We integrate 1 step at a time, but not only we do this, we also modify then the covariance step at each time in this sense. Let's say that we just have the exponential of a square power, the exponential of a fourth power with coefficient mu h and lambda h scale depending, and then some remainder term. The quadratic term is in principle very problematic. So the way one can deal with it is simply to reabsorbing it into covariance. So our covariance chim less than h get rested up. It now includes also a new term. And when we do the next step, we won't start with the covariance c minus h, but with a new Darcy covariance, which also changes. And I believe this is really non-standard idea, which is not common in mathematics. In many cases, when one deal with multi-scale analysis in both numerical or other problems in PDEs, one does simply a decomposition, but then doesn't do this iterative change, which really is important because what is important? Because I mean it's really fundamental because if it allows you to study these objects, even if the limit in the end is a completely different measure. So even if in the end the measure that you obtain is not absolutely continuous, it's not comparable to the original Gaussian measure, since you are gradually changing it, you can still study it rigorously. While if you say at the beginning, I choose a measure, decompose it into scale, and then I do step by step without ever changing the measure, and then you are forced to already know what we're expanding about. While in this way, you can do an iterative choice. So each step gradually changing, and in the end, you can also construct a limit where the limiting measure is not absolutely continuous with respect to any, I don't know, non-Gaussian measure. And this is, I believe, is very crucial. So the inclusion into the Gaussian of new parts. And then there is, of course, the lambda term, which we are still not talking about. And it can, in principle, the idea is that in principle it could do anything. It could grow indefinitely, it could go to zero, stabilize to a non-zero value, oscillate. And the only way to know in which case we are in is to study it explicitly, at least to some degree. So the most in this case, so in the case of title 4 to in 4 dimension, one can do some perturbative computation. What does it mean to do perturbative computations? And now we know it means to use truncate exponential at some degree, use Wick theorem, take all the terms till one order and put the rest in some remainder to be estimated and say that it is small. But at second order, the idea is that one can get the new coefficient. So if we integrate with at scale h and we get a new coefficient in front of the lambda to the fourth, this new coefficient is the same as before minus something. And this minus something is proportional to the square of the original. And if we want to recursive relation, lambda is to minus one. I consider negative edges. So it goes to minus infinity edge. If we find relation, we see that, let's say also C equal to 1, we see that the solution is, I mean, simply 1 over H. Correct, but if take 1 over H minus 1 over, no, I'm getting that.
It should be, for instance, lambda 0 over 1 plus lambda 0 H.
No, sorry?
Lambda 0 over 1 plus lambda 0 H. This will give a solution of the continuum that this lambda system. But I mean, it's three problems and SSE problems.
Okay, and so we can see that yet it goes to 0.
Minus lambda 0 H because H is 9.
So, yeah, you're right. We can see that it goes to 0, but slowly. I mean, I see the logarithmically, of course, this is not a logarithm. The problem, I mean, this is terminology. Usually, if one has a behavior like into the H, one says that this is polynomial. And then if one has a polynomial in H, one says that it's logarithmic. Yeah, it's very good terminology. So what I want to say that is we have a polynomial in H, not in L in the volume. This is called logarithmically. Behavior, so it goes very slowly to zero. So in the end, at least with the 5 to the 4 measure on a lattice without taking continuum limits, the real problem is just to estimate the remainder, which is not an easy problem, by the way, but it is doable. No, it's doable. So please, it's a fact. Please be optimist. Sorry, no, I quoted the results, but yeah, okay. Huh? Very nice, very nice. So now you are ready to tackle the papers. So I want to convey these ideas, because they can be helpful to people working in many different areas. Whenever you have a problem which can be restated, a problem maybe involving many degrees of freedom, which can be restated at a perturbation around a nice but singular object. So nicer in the sense that it allows a good multi-scale decomposition, but still singular. The renormalization group paradigm or circular ideas can be really helpful and really be the way to tackle these kind of problems. And the steps are the following. First, you have to choose a way to decompose it. So if you have a Gaussian, you have to find where are the singularities and decompose around them into slices. And of course, this decomposition may be done just maybe partly a priori, and then you have to adapt it by the way. Second, you have to consider the interaction, I mean, the part that you are integrating, and see which are the problematic part and make them as explicit as possible to say, okay, these are the problematic part, and I really have to track them into along the iteration. And then the non-problematic part, you have to estimate them. And to estimate them, you actually have many opportunities because if you are in a regime where you choose the original lambda, for instance, the original parameters to be small, you can use them to control something, especially if you expand in higher order, then you have higher orders of these small parameters, and maybe you can use them. If you at contribution which are far away, you maybe can use the decay of the covariance, because usually, at least on a single slice, the covariance matrix has good decay properties at long distances on a single slice. It's singular when you sum all the contribution. It's singular the original one, but the single scale should decay very well. And that's also one reason to do the composition. And you can use them. And then you could use also the fact that some terms are irrelevant and you know that they scale well and tends to become smaller and smaller. So you have a different way to obtain good decays, and the various approaches basically are different in the way that you cook up a way to estimate the remainder, because you have many contribution, many way to have a smaller contribution, and so have some flexibility. And it really depends on what you want to obtain and the problem at hand. So many approaches have been developed in years. The one, maybe the original one that started it all, was the study of phi4 in 3 dimension and infinite volume through what was called a phase cell expansion, which is basically this idea formalized at the basic level. So it's a decomposition both in volume, where one considers blocks in the X space and in Fourier space. So one decomposes the covariance in slices depending on the momenta, and then you consider various boxes inside your lattice of different volumes at each step. And combining them is called phase cell expansion, because the phase space contains both momenta and positions. This technique was greatly expanded and refined by Bartol first and then Feldman, Manier, Rivasol Senior, and they actually applied it to feed the four in 4 dimensions and on the lattice. So this was one example of taking this program and really applying it till the end. Of course, the paper is not super simple, and and of course, it's very old when a paper tended to be very short, condensing all kind of information in 2 lines, and this might be taken into account. And also, this was actually the second approach, but was more similar to the older one. Another approach, which was still applied to the fit to the four theory on the lattice, was by Gawetsky and Kupiainen. And this was really based on the averaging idea in X space. So taking a block, taking the average, and going on to the next step. And this technique was greatly refined and applied by Bridges and collaborators and in many different problems. So let's say that this now technique by Bridges is now the newest one, the cool one, I don't know, the most modern one, maybe, at least for this bosonic business. There is also an Italian school grown around Galavotti and many of its collaborators, which are also well represented in SISSA and in this room, which dealt mainly but with fermionic system, that is with determinants and so on. I mean, originally it tried to tackle the bosonic problems, and then it had much more success and focus on fermionic problems, which, I mean, they are in some sense simpler, but not so much. But and also they are or representing an application to matter physics, condensed matter physics, and so this is a very very short list of application just to the 5 to the 4 theory, and I think that's one because again it started as an approach to 5 to the 4, and then had much more success with the fermionic theories. Of course, there is a really big part of the literature that I'm not putting here, and maybe there's the Bauerban technique. Who said you said okay? There is this also this technique by Bauerban, which is like the Graal. I mean, no, almost nobody knows it. It's screaming mysterious, and it should be the one technique, the final one, the ultimate one, that when you master, you can tackle all the problems, even the one with the big lambda and so on. And that's it. This concludes our short overview. I mean, I think that while there are difficulties and so on, one of the method is still in its infancy. Most of the time, each people that try to apply it starts again from scratches instead of, and one of the reasons is that there are few people actually doing mathematical rigorous version of it. So there is not really a community. There are single persons, single people scattered across the globe doing something and then having to rediscover the wheel each time. And maybe one reason for this is that also it tackled mostly problems with arising from quantum field theory and statistical or condensed matter physics, but in principle it could be applied to any problems wherever elliptic operators arise. And so it could be applied in calculus operation, which they are almost all everything about elliptic operators, dispersive equation when one has maybe an elliptic operators, but in imaginary time with an imaginary coefficient. And so in fluid dynamics, where really there is this reason of energy that goes from higher to lower scale and smaller vortices, and then to the kinetic scale, and so turbulence, and also the numerical counterparts. Maybe it could be some ideas could enter into improving numerical methods in studying fluid dynamical systems, so some kind of separate multi-scale simulations and then putting it all together, or maybe this idea could be useful in other ways. I don't know. So I believe it could be really an impulse to the research if this method found application also in other areas where there is a bigger public. And that's it. That's all I wanted to say. I thank you.
Already some discussion during the seminar. If there is another quick question, it's time for it. Questions from all? We are for more. If it's not the case, I suggest we can thank Fabrizio again.
And let's go to the bar.
Thank you.
Thank you.